This is a video made up by Adrian,
Alex, Bruno,
Juanpi, and me, Daniel.
and welcome to our activity 2 of physics.
Hello guys, and welcome to a new physics video where we're going to talk to you about waves and we're going to answer some questions related to them.
First of all, we're going to talk about what a wave is. Well, a wave is what we call an oscillation or periodic motion, but in nature as sea waves, sunlight waves, sound waves, etc. All waves transfer energy but not matter. That's why plastic ducks in the bath stay static in the same place, even where there are waves.
Oh, rubber ducky, you're the one.
Some waves need a medium to travel and others not. The sound needs air, and sunlight travels through the empty space. In those that need a medium like the sound, the speed in which they travel depends on the medium. The denser the medium is, the faster it travels, because the molecules in which it travels are more together but it less endures and vice versa. And now, which are the different ways that we consider sound can be transmitted? Well, providing examples, first of all we have the water. That's why the sings of a whale can be listened and measured. Then we have the metal. When you hit a metal tube, you create a perturbance which generates waves of sound that travels through the metal and creates that characteristic sound. Another example could be the gas. We use it every day. The air is a gas that the sound uses to travel and that makes us able to talk and to listen music. Now we're going to talk about some properties of a wave. First of all, we have the reflection. The reflection is when the wave gets to a body that doesn't let the wave continue with its propagation, so it gets back to the medium in which it was traveling and changes its direction, or in other words, it gets reflected, but when it gets to the body, the wave transfers part of the energy to the body, but its velocity and frequency remains the same. A common example is the echo sound that we hear in empty places and hills. Another property of a wave is the refraction. It's like when waves get to a separation line that divides two mediums in which they can travel, and then the wave divides or refracts, and part of the energy goes to one medium and the other to a different medium. The frequency remains the same, but the velocity and therefore the wavelength depends on the medium in which the refracted wave is. This can be experienced when hot and cold air are in the middle of someone's conversation, and it will be more difficult to communicate due to the wave's deviation. Now the diffraction. This happens when the wave gets to an object and the wavelength is equal or bigger to the object, and the wave changes its direction if the object emitted a spherical wave. When the object is equal, the shadows that the waves form over the object's borders are perfect, but when it's considerably bigger, the waves go in all directions and with a bigger range diffusing the shadows. That's why radio signals have enormous wavelengths, so their information goes to a lot of places in a big range using the buildings as the object. Now we have the interference. When two transmitters of waves are in the same place, the interference among waves can happen due to several conditions as the coincidence of their maximum amplitudes producing a constructive interference, and as when their maximum amplitude is the same but in different directions, they produce a destructive interference. What is a mechanical wave? We are going to give this definition with an example. A mechanical wave is the one that needs a medium to propagate, such as sound, waves in sea, earthquakes waves, or the ones that appear in the skin of someone when they get a punch in the face.
Freaks fly together.
Now we're going to make a comparison between a transverse wave and a longitudinal wave, and we're going to give an example of each one of them. The transverse wave happens when the particles in a medium vibrate perpendicular to the direction of the wave's motion. An example could be when a drop of water falls in a fluid. The ones that are formed when a heavy truck passes fast next to us, or this.
Stop it. Get some help.
Now, the longitudinal wave happens when the particles in a medium vibrate in the same direction of the wave's motion. An example could be when the sound travels through air and compress and decompress the particles of air. This can be explained with the next object. Now, the formulas to calculate the speed of propagation and frequencies of a transverse and longitudinal wave are, and in resonance are. And now, for the second part of the activity, we're going to listen to Adrian and his explanation with the simulator of FED Colorado software. Adrian, here you go.
Well, so here begins part number 2. We have to use a simulator with the next characteristics. The simulator is about waves. Here we have it. We have an amplitude of 0.5 centimeters, a frequency of 1.5 Hz, damping known, tension high, roller, timer, slow motion, fixed temp, and oscillate. We are going to start the simulation. We have to stop the simulation at 3.5 seconds. Of course, we have it in slow motion to get a more accurate result, or at least approximately. The release, we have it, and we have to now count the notes. The notes are 1, 2, and 3. But actually, we have to calculate the velocity and wavelength of this simulation. So, we have to count also the antinodes, which are 1, 2, 3, and 4. We put here 3 notes, and in the calculations we are going to use 4 antinodes. Here we have it. We have an amplitude of 3.6 centimeters in spread velocity, or velocity of the wave, of 5.4 centimeters over second. Now we move to the next simulation. It's just the same as the last one, but now just the amplitude changes. We have to stop it once more again in 3.5 seconds. The frequency does not change, which means either the wavelength and velocity are going to change. So here we have it. Once more again, like I said, we have 3 notes and 4 antinodes. So the calculations are going to be the same. Oh, one thing I forgot to mention. The length is going to be always the same in all of them, because the port of the simulator has the same length always. Or if you change manual or pulse, it changes, but in fixed temp it's always 7.2 centimeters of length. Now we move to the third simulation. Here the amplitude goes back to 0.5 centimeters. The frequency is now changes to 1.8 Hz, and with this I know that the wavelength and velocity are going to change, because frequency of and wavelength are inversely proportional, which means that when there's more frequency, the wavelength is going to be less. Once more again, we have to stop it at 3.5 seconds. And there it is. Now we have here that there's 4 antinodes, but now we have 4 nodes. And as we can see, if we compare it to the other waves, we can see that here there's like a little bit part of extra extra antinote, it will be like 0.15 centimeters. And we apply this to the calculations. We use the same calculations, but now with the 0.15 added, and we get a lower wavelength due to the inversely proportional thing, and the velocity is going to be bigger. So this was part number 2, and I hope you like it.
Well, that's all. We hope you enjoyed our video. Thank you so much for watching and see you next time. Goodbye.